Hello, my name is Don Halcomb. My profession was in engineering. A while back I became interested in the depletion of worldwide energy resources. I decided to make a movie about these events. Many others have examined this subject with an historical approach or from the view of economics. I will do neither. My observations led me to believe that most of the talking heads on TV and in other documentaries were just wringing their hands over the subject and offering no viable solutions. I'm going to attempt to outline the whys and the why nots of a path to the future. This treatment will give scientific reasons for what should not be done and other reasons for what must be done. I will use a little history in the prologue to this subject, but I promise it will be short. A bit more than 200 years ago, a fellow named Thomas Malthus became interested in the factors that affected population stability or growth. I start with an excerpt from his analysis. I'm going to allow 60 seconds to read this slide. The second bit of history concerns the subject that Malthus studied. It is the population of the Earth since 1800. The third part of history is the consumption of energy since 1820. From here on, the subject will be about the last two graphs and their ramifications. I hope you noted the similarity of the two graphs. It is no accident that they are shaped the same. One is the creator of the other. These two graphs are the crux of our predicament. It has been said that past is prologue. That is not totally true. On a planet with finite resources, the past is not always the prologue. Many people have an innate belief that population and economies can expand forever. Without resources, that is a pipe dream. Some of the people watching this have no real feeling for the meaning of energy units. A metric unit of energy is the joule. It is hard to grasp what this means for many people. Another way of expressing energy is power. Power is the measurement of energy per unit time. 1 joule per second is a watt. The watt may be more useful for most of us because practically all of us grew up using filament light bulbs that were rated in watts. We all have some feel for a 25-watt light bulb, or a 100-watt light bulb, or a 1,000-watt light bulb, and can somewhat visualize their power outputs in a way that we can intuitively feel. It is time for a little game. Imagine a 100-watt filament light bulb. Turn it on at midnight, December 31st. Let it run continuously every second of every hour of every day until midnight of the next December 31st. Shut it off. That bulb just consumed about 3.16 billion joules. Now it is time for a serious game. Add up all of the energy consumed on the Earth in a particular year. use all the energy from coal, oil, natural gas, nuclear, geothermal, solar, wind, and fuels made from biomass. Make sure that all of the units for each are in joules. Divide the sum that you get by the number of seconds in 1 year. The answer you get is the yearly average power consumption for the planet in watts for the year's data that was just used. This answer is a very large number. It is in the order of trillions of watts. For the year 2010, all of the people on Earth consumed about a yearly average of 17 terawatts of power. In order to simplify life a bit, let us take the yearly average watts of power used by mankind for the year of its use and divide that number by the population of the Earth at that time. What we get is the average power consumption per capita, or person. Now we get numbers for which everyone can probably have an intuitive feel. This graph is based upon these calculations. These data show, without equivocation, the consumption of energy grew faster than the population of the Earth. This should not surprise anyone. Did the year 1800 have any trains, cars, trucks, airplanes, televisions, cell phones, industrial agriculture, and the infrastructure to support all of these? The answer is obviously no. What happens when we run out of fossil fuels that are worth recovering? We are living in a population bubble that is being fed by an energy bubble. The evidence indicates that the energy bubble is the direct cause of the population growth. Else, why the low population before the year 1800? Remember Malthus. These are the resources that he did not know existed. These resources are finite. For the year 2010, our energy consumption was about 81% coal, oil, and natural gas. The rest consisted roughly of 10% biomass, 6% nuclear, 2% hydro, and 1% solar, wind, and geothermal. You can tell which one is carrying the most load. To finish our history lesson, we must think about a concept called infrastructure. What is infrastructure? It is more than you may initially believe it to be. Science has created an infrastructure that is almost totally dependent upon fossil fuels, which is 81% of our total energy consumption. Literally, almost everything in our world is dependent upon fossil fuels. Practically all forms of transportation, agriculture, manufacturing, construction, communications, the power grid, raw materials would cease without fossil fuels. The entire world as we know it would have to be replaced with an entirely new infrastructure. All this would require the greatest changes since the founding of civilization. I do not exaggerate. The first subject for scientific evaluation is about biodiesel fuel for diesel engines, jet aircraft, trucking, tractors, and marine vessels. This type of fuel is the common cooking oil used in our homes and restaurants. It is extracted from plant matter which is grown all over the world. For those that know a little chemistry, the process that produces it looks like this. This chemistry is presented in a general form for various starting sources. It uses the general symbol R for hydrocarbon chains connected to the central core of the molecules. Methanol is reacted with the starting triglyceride to produce a methyl ester plus glycerol. It is the methyl ester that is the biodiesel fuel. Note that the starting triglyceride and final methyl ester differ only with respect to 4 hydrogen atoms. This means that the starting weight of the triglyceride and the final weight of the methyl ester are almost the same. In future calculations, we will assume they are the same. It makes life a lot simpler. The plants that produce triglyceride are numerous. I obtained some tables which started with the world production rates of different sources of triglyceride and determined the agricultural land area required to produce it. I obtained data for the total current yearly consumption of diesel, jet fuel, and kerosene. I present these data in the next tables. Table 4 is the 2007-2008 yearly crop yield data for the major triglycerides. The left column lists the source. The second column is the yield in millions of metric tons. This is converted to the third column, which are the actual kilograms per year. The crop yield data for each kind is also given in the fourth column. This is in kilograms of triglyceride per hectare of agricultural land. The percentage of agricultural land used for each triglyceride is shown in column 5. The most important number for table 4 is the average kilograms of cooking oil produced per hectare of land, which is 786.6 kilograms per hectare. The total agricultural land used to grow the cooking oil is 1.613 E08 hectares, and the total agricultural land on the planet is 4.932 E09 hectares. This all means that about 3.27% of the world's agricultural land was used to grow triglycerides for the growing year of 2007-2008. I don't know about you, but this seems reasonable to me. Here is a slide that shows the increase in cooking oil production from the 2007-2008 season to the 2014-2015 season. There has been a growth in production of about 37%. This means that the percentage of agricultural land used for cooking oil since 2007-2008 would now be about 4.48%. Still looks reasonable. This table is important with respect to biodiesel. How much agricultural land would be required to produce enough biodiesel to replace the current jet fuel, diesel, and kerosene made from oil? Let's find out. Use an average of 786.6 kilograms of cooking oil per hectare for the world production rate. Use 1.522 e to the plus 12 kilograms for the yearly requirement of biodiesel. This means that the land requirement to produce the required cooking oil would be 1.935 e to the plus 09 hectares, or 39.23% of the total ag land. Our current land use for growing cooking oil is only about 4.5% of the total agricultural land. Remember that this does not cover any gasoline replacement. This calculation truly shows the limitation of our agricultural land. We must never use this much agricultural land to produce something that will just be burned up for fuel. With an ever-increasing population, we have to feed a lot of people. Always remember that the energy in biodiesel came from the sun. On a yearly basis, even sunshine is a limited quantity. One of our challenges is replacing fossil fuels with other portable fuels. The trick is to produce a fuel that does not consume DNA-produced hydrocarbons. It will surprise some to learn that nitrogen is by far the largest component of the Earth's atmosphere. A chemist named Fritz Haber invented a process that took nitrogen and hydrogen to form the compound ammonia. Ammonia is the starting material used to form ammonium nitrate, a fertilizer. The hydrogen used in the formation of ammonia does not occur free in nature. The current methods of making hydrogen are to hydrocrack portions of petroleum in an oil refinery, or to use methane and water to form carbon dioxide and hydrogen. In the future, these sources will no longer be available, as there will be virtually no fossil fuels. An electrolysis cell could be used to make hydrogen and oxygen from water. This process will consume a lot of energy. Liquid ammonia can be transported around in relatively low pressure tanks. Liquid ammonia has about the same density as gasoline. The energy content of about 3 gallons of liquid ammonia is equivalent to about 1 gallon of gasoline. Internal combustion engines can burn ammonia to replace gasoline. One blessing of using ammonia as a fuel is that it takes nitrogen from the atmosphere and then returns it back to the atmosphere when it is burned. The curse of using liquid ammonia as a portable fuel is that aviation may not survive. It would be difficult to carry enough ammonia fuel aboard in an airplane to fly very far. The current use of nuclear power is very wasteful. The plants are operated basically without the future in mind. Many of them just put their waste fuel rods underwater for storage and currently do not recover any fissile material that they contain. This is probably for sound reasons. To separate unused U-235 from 238 requires physical methods using centrifuges. To separate plutonium from uranium requires chemical methods. Both operations are very messy and costly. More important is that radioactive waste problems are monumental. This alone makes long-range nuclear power a dubious candidate for our future. Hanford, Washington is one of the most radioactive places on the planet because of these problems. Long-term storage of radioactive material is still a political football with no solution in sight. Let's forget all of that for the moment and investigate the most efficient but still messy method for using the remaining fissile nuclear fuel on the planet. The purpose of the next calculation is to see just how much power it could generate and how long the fuel supply could last with recycling. On this planet, there is only one naturally occurring fissile element, and that is uranium-235. Mankind has learned how to make 2 new fissile elements, and these are uranium-233 and plutonium-239. The fertile material U-238 is converted to fissile plutonium-239, and fertile thorium-232 material is converted to fissile uranium-233. Observe that one must sacrifice one fissile material to make another fissile material. There is no free lunch. There is a process that is called fast neutron breeder reactor technology. These plants use liquid sodium as coolant and are not the type of plant that we generally use today. I would like to use this type of plant to show the absolute maximum amount of power that could ever be generated by nuclear power, and the longest life that could be expected for the fuel used in such plants. Recycling would be used, but would still be a very messy process. This should reveal what we could get from nuclear using our wildest imagination. Our starting fertile material would be 7,250,000 metric tons of U-238 and 2,000,000 810,000 metric tons of thorium-232 for a total of 10 million metric tons of combined fertile material. The total starting sum of fissile U-235 and plutonium-239 would be 58,000 metric tons. You have been staring at the breeder reactor method all this time with its goal of reproducing new fissile material from fertile material. The plan is to take 10 years of power production time to generate new fissile material from the fertile material, then to recover the fissile material for a resupply. Now I am imagining 1,000 fast neutron breeder reactor plants, each charged with 58 metric tons of fissile material per plant. But I'm going to do the calculation as if one gigantic plant contained 58,000 metric tons of fissile material. Using the 10-year life of the fissile material in the gigantic reactor, we get that 5.8 thousand metric tons of fissile material react per year. This means that 5.8 E6 kilograms of fissile material react per year. Calculations reveal that all of the fissile material used over a 10-year period would yield 13.4 yearly average thermal terawatts of power. Converting this to electricity would yield 4.56 yearly average electrical terawatts of power. For comparison purposes, our planet's current total yearly average power consumption is 17.34 terawatts. Nuclear currently creates 0.97 yearly average terawatts of thermal energy, with only 0.33 yearly average terawatts of electrical power. Starting with 10 million metric tons of combined fertile material and consuming 5.8 thousand metric tons per year of fissile material gives a total life for this type of nuclear power production of 1,724 years, changing out each reactor every 10 years. This obviously assumes recycle in order to obtain fresh fissile material. This is certainly a long time, but the electrical power production is certainly not going to save our bacon. The liquid metal that is used for cooling the fast neutron breeder reactor is sodium. To get electrical power from such a plant would require a unique heat exchanger to pass the thermal energy in the sodium to water. The water is in the form of steam that would drive turbines to generate electricity. I personally would not want to be around such a plant. As far as I am concerned, nuclear power should not be in our future. Well, we've examined 3 replacements for fossil fuels, and none of them are out-and-out winners. Let's look at the big one. Sunshine has always been the king on planet Earth. It made all of the fossil fuels over 100 million years ago. What can it do for us in our future? Solar power can be thermoelectric or photovoltaic. This type of thermoelectric plant operates by focusing the light from many mirrors onto a central point where a liquid, or it could be a molten salt, is heated in pipes to eventually yield high-pressure steam through a heat exchanger. This high-pressure steam drives turbines to generate electricity, much like current coal-fired electric plants or nuclear plants. The thermal efficiency of such plants is the same for coal-fired or nuclear-heated electric plants. This efficiency is about 33%. This means that 33% of the sunshine energy is turned into electricity. Such plants require a lot of sunshine. Desert areas are prime places for such plants. Other climates with abundant sunshine will also be useful. This technology is not new. Other than the storage of molten salt, it requires little development. For this type of solar plant, the overreaching problem is that diffuse light cannot be focused. Solar photovoltaic panels will be one of the key sources of energy for our future. Electricity is generated directly from sunshine. These plants may look like this. Photovoltaic plants will most likely be built all over the earth and will not be restricted to non-arable land. They may even be built in urban areas. The total area of the planet Earth is 5.1 E14 square meters. The fraction of the Earth that is covered with land is 0.29. The world land area is equal to 0.29 times 5.1 E14, or 1.479 E14 square meters. This is the equivalent of about 36.5 billion acres. The surface area of Antarctica is about 1.4 E13 square meters. This is the equivalent of 3.5 billion acres. This means that the total usable land area is 36.5 minus 3.5, or 33 billion acres. This is close enough to the global land use pie chart value of 32 billion acres. We will accept the values of the percentages of all the land shown in the global land use pie chart. 33 billion acres is equivalent to 1.335 E14 square meter of total accessible land. Other data that was collected over many years by the National Renewable Energy Laboratory is shown in the average daily solar radiation map. It needs to be emphasized that this map is the solar energy falling on the solar panels and not the electricity put out by the panels. There is no finer source for this type of data, and it certainly reflects the real world. These data were collected over many years with large variations in the conditions. Averages are always better than peak event data. These data reflect the daylight, nighttime, and clouds in the measurements for an entire average day. The sun is also moving north and south during these measurements. The NREL also keeps track of the development of photovoltaic panels. This table gives the results. The efficiency of photovoltaic panels is of primary importance and is the ratio of electrical energy produced, measured in watts per square meter, divided by the incident light falling upon the cell, also measured in watts per square meter. A very good value would be about 1/3, or 33%. There are other losses, such as the conversion from DC to AC using an inverter. This is typically 95% efficient. There is about 98% efficiency for the transformation of low voltage AC to high voltage AC. This results in the overall efficiency from sunlight to high voltage AC current on the grid of about 31% overall efficiency. I prepared a table that compresses all of these data such that we can see the yearly average electric watts per square meter for any area we care to calculate. The urban land of the world, notice I said urban land, occupies about 9% of the total land area. This is about 1.202 E13 square meters. How much area is required to supply the total current use of 17.4 yearly average terawatts? The answer is assuming 6 kilowatt hours per square meter per day radiance, which is the equivalent to 77.5 yearly average electric watts per square meter. We take a number of 17.4 12 divided by 77.5, which is equal to 2.245 E11 square meters. This is about 1.87% of the world's urban area. This is amazingly small. The major problem with all forms of solar energy is they cannot generate electricity at night. There must be another independent source for the overnight period. The overnight source of electricity can be obtained by using thermoelectric plants to provide large amounts of stored molten salt. This would be used to heat water at night and provide high-pressure steam which would drive electric generators at night. The molten salt will be stored in very large, probably underground, insulated tanks. A heat exchanger will be used to generate the high-pressure steam at night. Normal high-pressure steam-driven turbines will be used to generate the nighttime electricity. The molten salt supply must be very large in order to meet other emergency periods. This requirement will make the use of solar power more expensive. These dual systems would have to be coordinated with the total electric grid in mind. The exploitation of shale oil and gas is currently in high gear. An examination of shale porosity is of interest for both oil and natural gas fracking. The porosity of shale will make many believe that we have copious quantities of oil and natural gas to recover from shale. The porosity for shale is about 20 plus or minus 5% at the depths where the drilling is usually conducted for fracking. These depths are about 9,000 to 15,000 feet. This means that about 20% of the volume of the shale rock could contain oil and or methane. At first glance, this looks like an enormous quantity, and in fact it is. The problem is that shale is a non-compressible rock. A practical example of what this means is to consider a normal sponge. If we soak oil into a sponge and then squeeze the sponge, we all know that the sponge would release a lot of oil. The question is why? A sponge is compressible. When we squeeze, its volume shrinks. Oil is an incompressible fluid. The volume shrinkage results in the pores of the sponge shrinking, which releases a lot of oil. Shale is an incompressible solid, which makes it a poor agent for oil recovery and gas recovery. Fracking uses methods that will only release about 5% of the shale's pore volume. Natural gas yields might be higher since gas is a compressible fluid and should be more prone to diffuse out of the shale pores. The life of a fracking well is about 1.5 years. During this period, multiple injections of high-pressure water containing surfactants, many are secret compounds, are sent down the well pipe to fracture more shale and release more oil or gas. To get more of the oil to release will require very fine shale particles. This would require enormous amounts of energy to break up the shale rock to smaller sizes. Fracking is a short-term, low-yield process. It will soon fade into oblivion. I wish that I could tell you in detail what the infrastructure will be in 2050. The UN predicts 9 billion people on the planet in 2050, and I predict a consumption of 3.32 yearly average kilowatts per capita. I am absolutely certain that the major share of energy for the planet will be supplied by various forms of solar power. Nuclear should be virtually past history, and the same for biodiesel. Practically all of our energy will be from electricity. This will still include hydro. the electric grid will become enormous. What will be the fuel for portable power? My guess is ammonia, but it certainly is not a given. I also guess that many of our old railway tracks will be reopened to every town above 5,000 in the USA. These tracks will not only be needed for passenger service, but for freight. Electric trains will be the only means for long-haul transportation of people and products. Local transportation will be electric automobiles. The future of aviation is certainly up for grabs. It is not clear as to how the ocean-going vessels will be fueled. Again, it might be ammonia. We must have some type of portable fuel for farming and construction. I'm sure that I've forgotten something. The most monumental problems lie in the arena of raw materials, drugs, herbicides, asphalt, and so on that were being made from oil products. I am sure that we can add to this almost endless list. The major mistake that must not be made is to run fossil fuels almost to dryness and then attempt to create a new infrastructure. This is the path to suicide. We will need the resources that we burned up to accomplish the new transformation. There's one attitude that we must all adopt. That is to stop trying to maintain the status quo. It cannot be done. Everything has to come to an end. Almost everything will have to change. It is fairly obvious that science must be the methods that are used to create the new infrastructure. Politicians, the military, bankers, and plutocrats are not equipped to do it. Global warming is considered by many to be the major problem concerning fossil fuels. Global warming may cause the oceans to rise in level and flood many coastal lands. More disasters may occur from storms created by higher than average atmospheric temperatures. These may cause loss of life and loss of property, but we currently endure such events. Tragedies like these will always be with us. Be warned that their frequency may increase. Carbon dioxide in the atmosphere exerts equilibrium states with other phases upon the planet. The major phase for a CO2 equilibrium with the atmosphere is water. Higher atmospheric CO2 produces higher concentrations of CO2 in the oceans and lakes. The history of the planet reveals that ice ages are quite common and occur in approximate cycles of about 100,000 years. When these occur, the oceans freeze over and the atmospheric CO2 drops to about 185 parts per million. Ice age cycles are much more common than greenhouse events. Why would the atmospheric CO2 drop with global ice formation? As the temperature of the lakes and oceans drop, the solubility of CO2 in liquid water increases. The temperature of freezing ice causes a virtually constant 185 parts per million of CO2 in the atmosphere when all of the surface water is finally frozen. By inference, when the ocean ice melts and its temperature climbs, then vast quantities of CO2 should be released back into the atmosphere. This is probably why it always came back to about 278 parts per million CO2 in the atmosphere. It is interesting that the rate of atmospheric CO2 increase was almost always faster than the decrease. This also implies that the heat-up rate is almost always faster from ice to very little ice than the cooling rate back to all ice. Greenhouse events have occurred in our past. These events are rare, but one occurred about 160 million years ago, and it was attributed to volcanism. There was a documentary movie made in 2007 called Crude: The Incredible Journey of Oil. This documentary traces the creation of oil that began about 160 million years ago. This was during the Jurassic period. The final point of that documentary was that mankind is making our own greenhouse, just like volcanism did during the Jurassic period. The global warming for the Jurassic greenhouse event began with an ice-free world. The Earth's landmass was shaped drastically different than it is now. It was called Pangaea. The land was one gigantic continent that was breaking up. Because of the breakup, massive volcanoes spewed magma as well as CO2 into the atmosphere for centuries. This produced high concentrations of CO2 in the atmosphere of about 1,000 parts per million. Without ice on the planet to produce ocean currents from thermal gradients, large parts of the oceans became stagnant. These stagnant waters, in conjunction with the high atmospheric CO2, pushed the temperature of the planet to new levels. This became a recipe for the rampant production of phytoplankton in the oceans. Phytoplankton, sometimes called algae, is a form of plant life that will grow near the surface of stagnant water. The water can be fresh or seawater. These growths are called blooms. Being plant life, they are made up of the same stuff we are. This means that they contain DNA, fats, oils, etc. Just like us, the phytoplankton go through life and death cycles. In the stagnant water conditions, they settle to the bottom. Nature abhors dead things and tends to attack it using other species that eat dead things and consume oxygen when the attack occurs. The consumption of oxygen is very important here. Cycle after cycle of algae growth then settles toward the bottom of the ocean. The decay occurs with the use of oxygen in the ocean water. This produces ocean water at the lower levels that is anoxic, meaning lacking in oxygen. Without oxygen, the decay ceases. Enormous quantities of dead algae in anoxic water were produced over time. With millions of years and other forms of sedimentation occurring, the dead algae were covered with mineral sediments. When the dead algae were covered with enough mineral sediment at the right pressure and temperature, oil was produced. This, of course, took millions of years. The paradox of our lives is that mankind appears to be repeating this cycle unaided. We are replacing the actions of the volcanoes of 160 million years ago. This is a weird way for nature to repeat itself. The acidity of the oceans and the freshwater lakes may be catastrophically altered by the higher carbon dioxide levels in the atmosphere. Higher CO2 concentrations in the atmosphere will shift the equilibrium concentrations of carbonic acid in the oceans and lakes. These pH changes, that's a measure of acidity, may be harmful to some of the creatures living in these waters. This may be the most serious problem of global warming. We are now talking about our food supply, which concerns everyone. This becomes an existential problem. When I began this movie, I promised a list of do's and don'ts. Well, here they come, and there is no priority since many of them may have to be accomplished simultaneously. Our enemy is time. Some believe that the remaining fossil fuels will last for hundreds of years. In fact, some will. The killer is this: we will eventually reach a point where it costs more energy to obtain fossil fuels than we get from them. That, folks, is a no-win situation. This is the best definition I know for when we have run out of fuel. Given that we ran through the lion's share in about 100 years, 1900 to about 2010, my estimate is it will be about 50 years before we hit the wall. The lion just keeps getting hungrier. The second half will go faster than the first half. I will begin with the do's. Remember, they are not listed in priority. To start the list, I begin with a crash program to develop and use non-carbon portable fuels. This goal is dual. It should help diminish global warming and also create fuel for our absolutely critical needs of farming, construction, marine, shipping, and aviation. I have suggested ammonia, but it has some drawbacks. Simultaneously overhaul the electric grid to adapt to solar power. This would include both photovoltaic and thermoelectric. Remember that night and day stuff? Next, promote, develop, and execute immediate and massive solar power. Put equal emphasis upon photovoltaic and thermoelectric. I would also include building thermoelectric plants all across the South. This would help the grid system. Next, start the development of raw materials replacement caused by the loss of fossil fuels. This may be very difficult and certainly is not quick. Next, try to decrease the consumption of fossil fuels as we replace them with solar. Finally, for the do's, stop any further investment in nuclear power. Now for the don'ts. Do not increase biodiesel production above the normal use of cooking oil. Agricultural land is too precious for that. This ends the movie. Thank you for having the patience to watch it. At least you did not have to endure any political or economic arguments.